Hello, 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 and welcome back to Shiksha DaCosta. Today we're going to learn where sinusoidal functions are applied in real life. And as part of this lesson, you're going to collect some sinusoidal data yourself. You're going to also identify whether that's periodic, and you're going to explain any restrictions that the situation has on the domain and range. So that's what that means, how to identify any limits on the domain or range of the data. And then we're going to take that data and we're going to explore it using some problem solving skills. To start off, let's look at this example of a theme park ride. So while they were on this ride, Rika used her phone's accelerometer to measure the g forces, or how much the force of gravity was pulling on her phone while she was on Cyclone, which is a ride at Canada's Wonderland, which is just north of Toronto in Ontario. And while she was on, when she got off the ride, she looked at her phone and the graph looked kind of like this. And the question to ponder here is, why would it look like this? What would be causing these waves? So here we have the time measured in seconds and the total number of g forces. Normally, when you're just sort of standing still, there is one g, one of Earth's gravity affecting you. So pause the video here and see if you can think about what might make the graph look like this. The way the ride works, just before you do pause it actually, the way the ride works is it swings back and forth slowly at first, and then it swings a bit wider. And while it's swinging, this arm here is rotating. So why would that create a graph like this? Pause the video right now and take a look. Well, hopefully you recognize that, okay, if this thing started to swing back and forth, the swinging motion would increase the number of g forces. And once it's reached the top of the swing, imagine you were just sort of on a big jump or at the top of a roller coaster. At the moment that you fall, actually, the g forces actually drop. And then while you're falling, they go really high up. So this increase might be the swing back down. And then, when it gets to the other side, oh, now the G forces are starting to drop again. And then right away, the swing back happens and they start to rise. And the reason that it might sort of go down and up might be explained by that. But the reason why these are larger and larger waves, it's probably explained by the fact that it starts to swing slowly at first, and then it swings really, really wide. So in total, if you were to go on Cyclone, it looks like you got, I'm going to count this as 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, and 13 swings in total from one end to the other. With the largest one happening, obviously, near the middle of the ride before the swinging starts to slow down. So this is an example of something that has created a wave pattern on a graph. Now this is not quite sinusoidal because the waves are not all of the exact same height, but here we see that that kind of similar pattern happens in a different situation than just a rotation, but rather a swinging of sort of like a pendulum. In this investigation, you can do something kind of similar and you can download an accelerometer app. And if you don't have one on your phone, you can scan this code if you have an Android, and that'll take you to an example of that kind of app. And use that app to measure the g forces on the phone when you are swinging it in a pendulum. And to do that, the easiest way would be to place it in a bag and then just grab the bag at the end and swing that phone back and forth. And then take a look at what the graph of that motion might look like. So I'll invite you to pause the video here, go look for a bag somewhere in your house, download the app on your phone, place it in the bag, and start to do this experiment yourself. Well, after I ran that experiment myself, this is the graph that was generated. So let's take a look at that. So over here, you can see that and for the first 3 seconds, the graph is all sorts of weird, and I think that's because I was just sort of trying to stuff it in the bag after I hit record, and then I started to actually swing it back and forth, And I tried to swing it back and forth in a really even way. So it's sort of reaching the same ends, the same point on the front and back swing. And if I once I did that, I noticed that that generated actually a sinusoidal wave. It's not perfect, of course, because my swings weren't perfectly the same every single time, but that wave pattern could be created by using a sinusoidal function. Here we can see that one of the things that generates a sine wave is not just rotation, but the swinging of a swinging motion, just like a pendulum or a swing. In this next investigation, you can go ahead and research the average amount of daylight in your city for each month and graph that by putting that on the y axis in minutes, the amount of daylight, and for the x axis, put the number of days since January 1st. And if the research, and throughout your research, if you only find it per month, then just assume the measurements were made at the end of the month. And once you've graphed that, take a look and see what you notice. Well, if you had some trouble finding that information, you can always use the data that I've collected. And when I looked this up, I went to a website called climate.top. And on that website, I was able to find the amount of sunshine, but I don't really care about sunshine. I care more about daylight. And the difference is sunlight might involve it might be cloudy and that might cover up the sun. But daylight just tells you how much for how long was the sun actually out. And so this right here is the data that I'm looking for. And I'm going to graph that. So first I'm going to use a table of values because I want to convert all of these to the same unit, not hours and minutes, but actually just total minutes. So in January, again, I assume that this was made at the end of the month. So on January 31st, there were 559 minutes of daylight. So 9 times 60 is 540 plus 19 minutes is 559. And I did that for all of these measurements. I found out what was the number of minutes of daylight at the end of that month. And now I'm going to try and graph that. In my graph, I don't know if you notice, but it sort of seems like a wave pattern, like a sine wave almost. How could we use this data? That's the next thing to consider. Why would anybody bother making a graph out of something like this? And what use could it serve? So I'll invite you right now to pause the video and ask yourself this question. What could we use this data or this graph for? Well, one thing that just came to mind for me is, hey, if I want to find out how much daylight there is tomorrow, all I have to do is find an equation that would create this graph. And then in my equation, just plug in the number of days that tomorrow has since January 1st, or the number of days that have passed between January 1st and tomorrow. And so in this lesson, we realized that sinusoidal data doesn't just happen when there's a circle rotating. It actually also happens whenever there's any oscillating motion. So any motion that's back and forth, just like a swinging pendulum. And if you find a situation like that, if you start to collect data and you graph it and it turns out to be sinusoidal, you can actually use the graph to come up with an equation that shows the relationship between those two things that you're measuring, the time and the height, for example, or the time and the g forces. And once you have that equation, you can use either the equation or the graph itself to ask, what can I learn from this? What can I use this data for? And then actually answer those questions. Now, the one thing to consider is now that we're connecting this to real life, this is an application of sinusoidal functions. The fact that this is a real situation might impact the domain or the range. And so we might need to limit that to show that, hey, this is the real world. And, the domain can't be any real number. For example, we might not be able to go to infinity or negative infinity. We might not even be able to have any negative numbers at all. In this example, we're using that graph here for the number of hours of daylight, and we're going to use this graph to find the number of minutes of daylight, that's d of t, where t is the number of days since January 1st. We're also going to look for the domain and the range of this function. And once we have that equation, we're going to try and answer the question, how much daylight would you expect on May 23rd? And so I'll invite you right now to pause the video and see if you can answer these questions. Well, hopefully you started with the fully transformed template of a sine function, and here we just need to know what a, k, c, and d are. That's how we create an equation. Now, looking at this graph, how can I find these values? Well, one thing is I know that the a value, or sorry, the c value, the midline, is right in the middle. And if I look at this wave, the top looks like it's about here, and I would estimate that to be around 925. And if I look at the bottom, this is 538, but it kind of seems like it's going, I don't know, maybe just a little bit like it's going to start swooping back up. So I'm going to estimate that this is going to have a minimum of 535. And your numbers for here might be different, but as long as you're getting a graph that sort of loosely resembles this, I think we'd still be okay. So the reason I picked out the maximum minimum is because I know the midline is right in between. And if I average these two numbers, I find the midline is at y equals 730. And so that is the value of C. Remember, C tells you the exact value of the midline. Well, if I know the midline and I know the maximum, I can also find the amplitude, right? The maximum of 925 minus the midline tells me the amplitude is 195. And so that would give me the value of A. Now, technically, A could be negative 195 as well. And I'll talk about how you know which one it's going to be in just a second. Now, if A was negative, that would mean the function is upside down. So there was a vertical reflection. But I'm going to assume that A is just positive, which means that there was no vertical reflection, and the sine wave normally starts on the midline, and it starts by increasing. So that looks like it would happen right about there. So that looks like that's where the sine wave increases, and normally it starts on the y-axis, but clearly this has been moved to the right, so the value of D would do that, and that's positive. And it looks like it has moved to the right. I want to estimate it's a little bit less than 100. So I would estimate, but it's pretty close. So I would say maybe 95 days. So the sine wave starts after 95 days and it starts by increasing. So the value of D would be 95. Finally, to find K, we need the period. And 360 divided by K would actually give us the period. And here I know because the period, this is a periodic function of the Earth rotating, so that would take a full 365 days for it to complete its orbit around the sun, which would sort of make this graph repeat itself. And we can even see here that the last date was 365. That implies that, okay, if 360 divided by k equals 365, if I cross multiply, so if I multiply both sides by k, and if I divide both sides by 365, that would cancel these out, and I'd end up finding that k is this fraction exactly, 360 over 365, which I could reduce. I don't think I'm going to just yet, but I could if I wanted. Now that I know my four variables, I know that my function, I'm going to change it from f of x to d of t, and so therefore the independent variable would be t. My function would be the d of t, the number of minutes of daylight after t days after January 1st, can be found by using this exact equation. And to test it out, I've taken this, and you can do it yourself and put it in Desmos and see if you get a graph that matches this one. And yes, in fact, mine does perfectly. The next thing to worry about is the domain and the range. Now, clearly, the domain, we're only measuring the amount of daylight after January 1st. That's when we started sort of measuring. And so the domain needs to be any number that's greater than 0. So any value of time that's greater than 0 would make sense here. We're not sure what the upper limit is. I don't know that the Earth will ever stop rotating around the sun. And so I'm just going to leave it as t is greater than or equal to 0. But because time is continuous, it can be measured with any real number that's as long as it's bigger than or equal to 0. The range tells you the maximum and the minimum number of daylight minutes. And here we can see that of course, I estimated that the minimum was 535 and the maximum was 925. So that is the range of this function d of t. Finally, we are asking how much daylight would you expect on May 23rd? And I'll even ask you, go ahead and pause it right now if you like and see if you can figure that out. Here's a little hint to help you in case you need it. So at the end of April, which was 120 days after January 1st, if I want to find out the number of hours of minutes of daylight on May 23rd, this day would be 23 days after the end of April, which is 120 days since January 1st. So if I take my 120th day, which is April 30th, and I add 23, I would get May 23rd. And so the value of t that I'm looking for, the number of days since January 1st on May 23rd, would be 143 days. And to find out the value of this function, to find out d of 143, I just plug 143 into t, just like you see here, and I can evaluate all of this to find that the amount of daylight at 143 days after January 1st is 873.40 minutes, which I can also convert if I like to find out that it's about 14 hours and 33 minutes of daylight. So that's how we might take a situation that involves sinusoidal, that would create a sinusoidal graph in real life and create an equation that would reflect that exact relationship and use that equation to pose and solve problems that involve that situation. If you like this video, please like, rate, subscribe, and join our mailing list. And you can find this lesson as well as practice questions, solutions, handouts, and more on our storefront. Thanks and have a great day.